Hello everybody and welcome back to the North Manchester STEM Sharing Network YouTube channel. Today we are going to be looking at observing over time. So today's skill is observing over time. And we've got two parts to think about here. We've got observation and we've got how often in time. So observation can be anything with our senses. We can observe by looking, we can watch something change shape, change size, change colour. We can observe by listening. We can listen out for a change in pitch or an additional noise. We can observe by smelling. We can smell definitely when something gives off a gas or is burning. We can observe by touching. Maybe the texture feels different. Maybe it's changed state from liquid to solid or something else. And there's other ways to observe. We can observe using scientific equipment. So we could observe the temperature using a thermometer. We can observe the mass using scales. Now for time, the only real limit is practicality. Thanks to simple technology on a phone or a computer, we can time seconds and divisions within seconds. We can time by hours, days, weeks, months, years, or even longer. So it's all about how often we time something. If we are going to time every 3 minutes, we must stick to those 3 minutes. Okay, for today's experiment, we are going to look at solids, liquids, and gases. And remember that when an object has more heat, it has more energy, and the particles move about more. So if a liquid is this, with the particles moving and flowing over each other, if it's given more energy, it moves, the particles move more, and they bounce off of the walls of the container they're in, being a gas. If a solid with particles that are packed tightly and only move a tiny bit is given more heat, it will become into a liquid, more energy, more movement. The opposite is also true. As something cools, it has less energy. So if we take a liquid with particles moving a bit and flowing over each other, and it's cooled, there's less movement, less energy, and it can form a solid, where there's only a bit of movement and the particles are packed tightly. So today we're going to look at freezing. And this is taking a liquid into a solid. And we can do this in the home with just a freezer. So our experiment today is going to look at different household liquids and how long it takes them to freeze. We're going to observe them over time by looking at them, feeling them, and poking into them to check that they are all solid all the way through, to see if they freeze slower than water, faster than water, or maybe not even at all in a household freezer. Household freezers are usually around about -19 or 20 degrees C. You can get much, much cooler than this, but we all pretty much have access to a freezer. So for today's practical element, I've gathered some liquids from around the house. We've got simple things like soy sauce, vinegar, then we've got thicker things like ketchup and mayo. We've got things from different rooms of the house, like body cream and hair conditioner. We've got fizzy pop, so a liquid but it's got those bubbles in. We've got paint and we've got all sorts of other things. And I want to be able to freeze these liquids and just observe them and see what happens. Now obviously we could use an ice cube tray, or you could use cupcake cases, especially if you have the silicone ones which are washable, reusable and won't disintegrate. But another practical way of doing it is to make a little trays out of foil and some kind of container. So I'm going to do that now. I've lined the box with foil and made little foil dividers so I can have 6 spaces, and now I'm going to need to put foil within those 6 spaces so that no liquid will escape. So because we all pretty much have experience of water freezing, we're going to use water as a control. So I'm going to fill 60 millilitres of water and put it into one of the sections, and then at least we can compare water freezing to the other substances. Now to make it fair, let's put the same volume of each liquid into each one. So I'm going to go for some strange ones like conditioner. And even though it's more viscous, I squeezed that out and I've got the same volume. Next up, washing up liquid. Vinegar. Pepsi. I wonder what will happen with the bubbles. So, now that we have, I can't tip it because it's liquid, our 6 liquids, it's important that we go and put it in the freezer and note the time down. Let's observe every 10 minutes and let's look, let's poke it with a cocktail stick and let's feel the surface. Okay, this is a situation after 10 minutes. If I shake the drawer a little, you can see that the vinegar, the water, the Pepsi and the oil are still liquid by the way that they flow with movement. Let's test the paint. Yep, that's exactly the same viscosity as liquid and it completely moves with a poke. Now let's test the conditioner. Yep, that is absolutely liquid still all the way through. This is after 20 minutes. You can still see these 4 are still wobbling. That's still as viscous as always, and so is that. 30 minutes. If you look carefully, there's a bit of solid vinegar, I guess vinegar ice, forming on the top. And we've got quite a bit of water ice. For Pepsi, we've got a good solid amount of ice, but we've still got liquid too. For washing up liquid, it's still completely liquid. For paint, the surface has gone hard, but within the paint it's still liquid. And for conditioner, it's exactly the same. 40 minutes, looking pretty exciting. So we've got some ice forming in the water and the vinegar, and the washing up liquid has a layer, and the Pepsi I think will probably get there first, and then the paint is feeling quite hard on the outside on most of the top layer, but we've got some liquid parts too. And then for the conditioner, that's nice. We've got a hard layer on the top, but it's still liquid inside. There wasn't really anything to show you at 50, so we're at 60 now, and I'd say Pepsi's nearly frozen. I can still poke through, but it's still nearly there. Vinegar's pretty much still as it was at the start, with a big ice crystal floating on top, but still liquid. Water's nearly ice. Again, with the washing up liquid, we're getting there. This is nice and solid on the top. How far down do we have to go to get liquid? So about halfway. It's still pretty good. Use either end. Conditioner is starting to feel a lot like the paint now. Yeah, I'd say the conditioner and the paint are about half frozen each. That's about half frozen, that's nearly there, and not much frozen at all. Fast forward to 90 minutes where there's stuff to show. So we've got Pepsi, solid, water, solid, washing up liquid, nearly solid, vinegar unchanged from our first or second observation. Paint feeling more solid, but still got liquid underneath, and conditioner feeling pretty much the same as paint. In fact, probably a little bit more solid than that. So we've got our last look for the day, and we're just seeing that the vinegar hasn't changed, and neither has the paint nor the conditioner. So in the time it takes water to freeze, Pepsi froze faster, and washing up liquid did freeze but slower, and paint and conditioner mostly froze but can still be kind of squished. It's more like a paste, like a very cold kind of gritty paste, and vinegar has remained a liquid. See if you can repeat this experiment and see what you come up with. I hope you enjoyed this video. If you'd like more, please subscribe for more in the series of scientific skills. Bye!